I'd like you to imagine that you're in this canoe, paddling down a river. It's a nice summer's day, and suddenly you spot this exotic fish swimming right alongside the boat. So naturally, you lean over to take a closer look. And as you do, the boat tips slightly. You're not concerned. You feel fairly stable. But what you don't realize is that now your friend in the back seat has also decided to lean over. And this brings the boat to a very precarious position, beyond which an irreversible transition takes place. You've probably worked out the transition I'm referring to. It certainly gets you closer to that fish, but let's be honest, it could make or break a friendship. Anyway, I'll let you make up the rest of that story for yourselves. The point is, this canoe possesses something known as a tipping point, a point where the dynamic behavior of a system suddenly changes, resulting in an abrupt shift to some contrasting stable state. And such a shift is known as a critical transition. Now, critical transitions can occur in systems far more complex than that of this canoe. Let me give you some examples. Financial crashes, epileptic seizures, disease outbreak, species extinction. Despite having widely different mechanisms, each of these events share one thing in common. They're a consequence of crossing a tipping point. So wouldn't it be fantastic if we could anticipate these tipping points before they arrive? Well, in this talk, we're going to see how these seemingly unpredictable transitions are actually more predictable than we think, due to some of the generic mathematical features that these systems exhibit as they approach a tipping point. But before I launch into how we might go about anticipating these transitions, we first need a brief understanding as to what drives them in the first place. And the key players here are feedback loops. We've all heard that painful squeal that can occur when a microphone gets in front of its own amplifier. This is an example of a positive feedback loop, as illustrated on the left of this slide. Any input to the microphone gets amplified, which in turn gets fed back into the microphone, which gets amplified, and so on, creating this runaway effect until the system reaches its painful limit. So in essence, a positive feedback loop refers to a process whereby change is self-enhancing, causing a system to run away with itself and lose control. Negative feedback, on the other hand, acts to counter change, and so in general promotes stability. Consider the thermostat that regulates the temperature of your house. As the house temperature drops below some threshold value, the thermostat kicks in and sends more power to the heaters, bringing the house temperature up. As that house temperature then goes above that prescribed threshold, the thermostat again reacts to this and reduces power to the heaters, bringing the temperature back down. And so this thermostat is providing a negative feedback loop that stabilizes the temperature of your house. Well, with regards to a critical transition, a positive feedback loop is the key ingredient, as you might imagine. These negative feedback loops tend to create these locally stable states that a system can sit in and trick us into thinking that a system is stable on a global scale. Well, in fact, these underlying positive feedback loops can create tipping points nearby. And when the system crosses one of these tipping points, this stabilizing negative feedback loop snaps, leaving the system to get swept away in this positive feedback loop towards the squealing microphone, towards the upturned canoe, towards the epidemic outbreak, etc. Well, the examples we've considered so far, we've been able to understand through a relatively descriptive means, and our intuition sort of tells us why these changes come about. However, nature and society possess some incredibly complex systems that can no longer be understood through basic intuition. Let me show you the reaction scheme for the cell cycle of budding yeast. I think we can all agree there's quite a lot going on here. This reaction scheme is comprised of a network of positive and negative feedback loops all interacting with each other in various ways. Suddenly, it becomes very difficult to see how the abundance of the SCF protein complex is affected by a change in the abundance of the cyclin 3 molecule, for example. The only way to capture these feedbacks in a rigorous way and so understand the qualitative behaviour of the system as a whole, is through the lens of mathematics. Using a mathematical framework allows us to map out the stability structure of this system and therefore see where the critical transitions are lurking. However, there is a caveat. In order to accurately predict critical transitions in this way, one would require a perfect knowledge of the system parameter values that characterize these interactions. And in reality, this simply isn't the case. Due to small uncertainties in these parameter values, the exact location of these tipping points is seldom known. So how do we go about predicting a critical transition if we don't know where the tipping points are? The answer to this question lies in complementing this model-based approach with a data-based approach that directly uses time series data of the system evolving to assess the system's resilience. But what do we mean by resilience? Do you think you could remove one of these Jenga bricks without the entire tower collapsing? On a more serious note, if we remove a particular species from an ecosystem, how well does that ecosystem sustain itself, if at all? If MMR vaccination rates across Canada drop by 5%, how safe is that population from a widespread measles outbreak? Answers to questions like these are directly dependent upon the resilience of the system in question. Where resilience is defined loosely as the ability for a system to recover following some disturbance. So clearly, in the early stages of this Jenga game, when the tower is small, it's relatively easy to draw a brick. The tower is fairly resilient. However, as the game increases, the tower becomes more susceptible to these external forces and more liable to a critical transition, and so its resilience decreases as the height of the tower increases. However, for these more complex systems that we care about, like the population and the ecosystem, it's much harder to assess this loss in resilience by eye. But fortunately, there is a universal property of complex systems as they approach tipping points, and that is that they take longer to recover following a disturbance. So their natural tendency to wobble begins to slow down. And there's a very technical term in the mathematical literature for this phenomena, that as a complex system approaches a tipping point, it slows down. And it's called critical slowing down. And critical slowing down is at the heart of many of the early warning signals that are being developed today to anticipate these critical transitions. Let me show you how this works in an example for a model of a fish population that is subjected to harvesting. This model was proposed actually way back in the 70s to explain how ecosystems can suddenly collapse when subjected to critical levels of harvesting. On the left here, this diagram simply shows us the stability structure of the system. The solid black lines are the stable states that the fish population can sit in for some given harvesting rate. So for a relatively low harvesting rate, where that green line is, we can see that the fish population are able to sustain themselves at a high abundance. This is a good state for the fish population and the fishing community. However, if you follow that black line down, you'll see that as we increase the harvesting rate, there is a critical point where that stable state ceases to exist. This is a tipping point. This is the point where that positive feedback loop kicks in and the fish population collapses to this low abundance, undesirable state. And this transition can come as quite a shock to the fishing community, because near to this tipping point, it only takes a very small increase in the harvesting rate for the fish population to suddenly collapse. Now let me show you how this would evolve in time. On the right here, we've got a time series of our fish population fluctuating about that desirable steady state, but now the harvesting rate is increasing. Well, from the time series, we can't tell that's approaching a tipping point, at the moment anyway. And you'll see that suddenly, as that harvesting rate crosses that tipping point, the fish population collapses. And it's this that we want to avoid. This is that critical transition. Okay, but There's a big problem here. We don't know exactly where that tipping point is. As I said earlier, those parameter values are not exactly known. So how do we go about anticipating this kind of transition? Well, we move to that data-based approach. Let me run that same time series again, but this time we're going to compute two statistical indicators, namely variance and autocorrelation. Now, simultaneous increases in the variance and autocorrelation correspond to a decrease in the resilience of the system. They're picking up on that critical slowing down that tells us when a system is approaching a tipping point. So here, the same time series running again, the fish population fluctuating about that state. But now we're computing these indicators directly from the time series of the system in question. And that increase is telling us we need to intervene. There's something going on here. The resilience of this system has gone too far down. And you'll see that right before the transition takes place, we get that final increase in those indicators. And we need to do something, but in this simulation, we didn't do anything. The harvesting rate went across the tipping point, and we get this scenario here. Something I find absolutely fascinating about tipping points is the fact that they can occur on such vastly different scales. Empirical studies have found tipping points right down on the microbial scale of yeast, all the way up to the planetary scale of our entire climate system. And in each of these studies, researchers found the telltale signs of an upcoming tipping point in the time series data right before the critical transition took place. So this is very promising work. However, I'll add that there's still important progress to be made before we use these indicators universally. Assessing the reliability of these indicators in different structures of complex systems is currently an active area of research in the complex systems community, and something that our team at the University of Waterloo are heavily involved in. We live in an age where humanity continues to apply increasing levels of stress to natural systems all over the globe, potentially bringing them to fatal tipping points. However, at the same time, we are now more equipped to obtain data at a higher frequency and at a higher resolution, making any early warning signals that we develop more efficient, more reliable. So I strongly believe that the collaboration of mathematics with the natural and social sciences will play a key part in making sure that we as a society do not collectively tip the canoes of Mother Nature into catastrophic states. Thank you very much for your attention.